Hello and welcome to our demo video on the SCISSOR N3. My name is Imogen Anastasiou and I'm the product manager of the SCISSOR system. Today I want to give you a demo of the system, how it works, how it fits together and how to operate it. In today's session I'll give a bit of an introduction on subcutaneous drug delivery in general and the challenges with current drug testing methods, how we use the SCISSOR platform to tackle some of those challenges, and a short demonstration of the SCISSOR N3 in action. So, subcutaneous drug delivery involves injecting a drug or a formulation directly into the subcutaneous space, which is the layer just below the epidermis and the dermis of the skin. Many drugs are intended for injection from a medical professional via the intravenous route of delivery. However, in recent years, the subcutaneous method of delivery has become increasingly popular. With subcutaneous injections, it gives back that power to the patients, allowing them to self-administer their medication at home. Also, there's been an increase in insoluble and long-acting drugs on the market, which are ideal for subcutaneous drug delivery due to the nature of the subcutaneous space, which aids in the slow delivery of drugs over time, allowing for a more sustained release of that drug. All drugs that will eventually hit the market to treat patients will normally go through thorough testing in order to ensure efficacy and safety. This normally involves many different testing methods, as often it takes a very long time before the drug eventually gets to the patient that needs it. However, there is currently no standard in vitro practice imposed for testing of subcutaneous formulations. So, with oral formulations, we have certain USP standard practices, for example, but for subcutaneous delivery, there's a real lack of standardized in vitro methodology and techniques employed. So scientists often still use the USP2 or USP4 in vitro methodology for subcutaneous drugs to try and find an early insight of the formulation performance, but it doesn't really give the full picture of the events occurring, and it also tends not to reflect the in vivo situation properly, as they lack the biorelevant information needed for that decision making. Similarly, animal models are known to provide poor representation of the human in vivo environment, with bioavailability values obtained from animal studies varying wildly from the eventual human in vivo data, with even animal models in mini pigs and primates still differing significantly from humans. And animal studies are also very costly and time-consuming for companies, with the obvious ethical implications of using animal models also being a factor in these experiments too. And this is why we've created the SCISSOR system as a platform to simulate subcutaneous injection in vitro. The SCISSOR is used to help scientists bridge that gap between the standard rudimentary dissolution methods and the in vivo PK studies in animals. The system aims to reduce animal testing with those unrepresentative in vivo models, helping to reduce costs in the process. It also helps to speed up the drug development process as a whole, giving a fuller understanding of the formulation earlier in the development process, meaning scientists can excipient screen, rank order formulations, and make success or failure decisions earlier on, which formulations to scrap and which to continue in development, reducing the likelihood of those late-stage failures which are costly and both time-consuming. There are some knowns when it comes to subcutaneous drug delivery. We know the pH of the subcutaneous space, the relative temperature, we know the general ionic composition of the interstitial fluid, and we know the components of the extracellular matrix. We also know that a lot of these characteristics can have an impact on the drug upon delivery, which could then impact the eventual bioavailability of the drug. We've tried to incorporate as many of these knowns into the platform to better reflect the human in vivo situation. And this image is the SCISSOR system at its core. So it's a 3-chamber system allowing for 3 separate subcutaneous injection assays to run simultaneously or independently. We use this system to compare and rank order a variety of subcutaneous formulations, including solutions, suspensions, in situ forming gels, and many more. So, how does the system work? It works by incorporating a cartridge, which is filled with an artificial extracellular matrix. This is simulating the subcutaneous environment in the system. We inject our pharmaceutical inside the cartridge via a hypodermic needle, and the formulation will then diffuse through that matrix and out via these customized dialysis membranes on the front and the back of the cartridge, out into the chamber environment, which is containing a bicarbonate-based buffer simulating the interstitial fluid. We can then use our rainbow in situ UV fiber optic probes to quantify the amount of drug that has reached the outer chamber in real time, indicating uptake to the blood and lymphatic vessels. We also know how important the conditions are for comparing formulations, so the system is kept under physiological conditions for the assays at 34 degrees centigrade via a thermocouple and a hot plate, and at pH 7.4 via automated external CO2 influx. We also have stirring action in the chamber as well as external fluidics, ensuring homogeneity of the chamber buffer for reliable data analysis. The system also monitors the pH at the injection sites to observe any pH stresses on the formulation, and we also have turbidity sensors and cameras for each of the chambers to observe the presence of any physical instability of the formulation upon injection and over time. The release data, coupled with the turbidity, pH, and imaging data, helps gain a fuller picture of what's happening to your drug upon injection, and it also indicates how these events will affect the uptake of your drug in vivo. And we can go ahead now and we can have a look at the system in action, see the parts, how they fit together, and how this couples with our rainbow technology. Today we'll look at the SCISSOR N3 coupled with the Rainbow R6 technology, and we'll give you an overview of the system, how it works, and how it's put together. On the left-hand side, we have the Rainbow R6, and on the right-hand side, we have the SCISSOR N3 system. The SCISSOR allows for 3 assays to be run independently or simultaneously at the same time. The system comes with a camera for each individual chamber, and this allows us to understand what's happening to the formulation upon injection and to keep an eye on that formulation over time to give us an idea of the fate of that biopharmaceutical upon injection. We also have a backlight behind the chambers in order to create those crisp photos with the cameras as well. And we have a locating ring, which sits just above the heater plate on each of the chamber positions, and this allows us to change the chamber size to a small or a large vessel. We have external fluidics, which are running throughout the assay, and these are taking the liquid from the assay out to external flow-through vials to allow for sampling, and then they come back in a closed-loop system. We then also have a cartridge holder, thermocouple, chamber pH electrode, and cartridge pH electrode. We then have our cartridge holder, and this is where our cartridge filled with our artificial extracellular matrix will sit. And we have LEDs and diodes on either side of the cartridge, allowing for light transmission or turbidity to be measured throughout the assay over time. And this is looking for that physical instability of your formulation upon injection, any precipitation or aggregation events that may occur. Here we have the port where we inject our sample, the port for our cartridge electrode, and our chamber electrode. For ease of use, everything is in one position and we can just lift the chamber lids up to get hold of the items underneath. This is the small vessel size. This is a small chamber at 60 milliliters in size, and we can just lower our chamber lid straight into that vessel. And this is our larger vessel size. This is the 300 milliliter chamber size. And both of the chambers are filled with a bicarbonate-based buffer, simulating the interstitial fluid in vivo in humans. And that buffer is kept at pH 7.4 via the external CO2 bubbling for the duration of the assays. And here we can see the external rack where our flow-through vials head to, and this is where we would take our samples, or this would normally go to an external robot for auto-sampling as well. This is our locating ring, which we sit in just before we put our 60 ml chambers in place. This allows for proper heat conduction for our smaller chamber sizes. We're then going to fill our chambers with the 60 milliliters of the bicarbonate buffer, as well as a stirrer bar which comes with the chamber as well, to allow proper homogeneous environment inside that chamber. With the stirring action and the external flow rate, we have a good mixing of the external fluid inside the chamber, allowing that environment to remain homogeneous so that we can quantify how much of our API actually is released from our cartridge to our outer chamber over time. At the heart of the system is our cartridge, and this is filled with an artificial extracellular matrix simulating the subcutaneous space in vivo in humans. So it's completely artificial, it's a fully in vitro system, and we take our cartridge and we fill this with our pre-made extracellular matrix. Our cartridge has a membrane on the front and back, which allows for that diffusion through that dialysis membrane. And we have a hole on the top of the cartridge to allow the cartridge electrode to fit inside. And this is our matrix. This is our extracellular matrix, which is transparent to allow for proper light transmission. And we simply fill our matrix into the cartridge, allowing us to do that slowly so we don't have any bubble formation over time. Once full, we carefully place the lid on, allowing for the hole and the lid to be facing the correct orientation to allow for the pH probe to sit inside the cartridge. And that pH probe just sits just at the top of the cartridge, just at the site of injection. We then take the cartridge over to the system and remove the probe holder from the cartridge holder and place the cartridge inside. We can then do this for all of the other cartridges, lifting the lids, sliding the cartridges in place, and putting the probe holder back on top. So in this scenario, the cartridge acts as the subcutaneous space, and the outer chamber acts as the interstitial fluid or the uptake to the blood and lymphatic vessels. So if we look here, we can see us entering the cartridge into the cartridge holder. and then putting the probe holder back in place and securing with the pins. So then we want to take our electrodes over to the system, and we want to make sure those are calibrated properly as well. So we calibrate those via the SCISSOR N3 software, and these are also the same two electrodes for the cartridge and the chamber. So the chamber electrode will sit in the left-hand side port in the green section of the cartridge holder, and this will measure the pH inside the bicarbonate buffer in the chamber, and then this will sensor to the system when to allow the CO2 burst to help mediate the pH of the chamber. The cartridge electrode will sit just at the top of the cartridge to measure the pH at the injection site just upon injection, and this will monitor throughout the assay as well. We want to make sure we put our thermocouple into each of the buffers so that when we're taking the pH calibration, it's all accurate. And when we go over to our software, we'll go to our Chambers tab and see all of our connected chambers to the system, and we'll calibrate at pH 4 for all of the electrodes involved. We'll then go back to the system and we'll swap out the electrodes into pH 10 solution, giving them a rinse in between, and then we'll repeat the calibration in pH 10 as well. We want to create a slope for the electrode calibration between the pH 4 and the pH 10, with our working pH normally around physiological 7.4. It's important that we do a pH calibration before every assay that we run, just to make sure that the electrodes are responding correctly and that they're properly interpreting the pH values that they're reading. And then we want to make sure our electrodes are calibrated properly, that the millivolts are within range for the pH 4 and the pH 10, allowing us to have a good slope for those electrodes as well. And then we'll rinse the electrodes again before putting them in the system. So then we need to remove the electrodes and put them in the assay positions with the chamber electrode inside the cartridge holder in the green section on the left-hand side, and with the cartridge electrode inside the center of the system, reaching into the cartridge. So then if we look from the top, we can see both electrodes in place, as well as the thermocouple as well on the right-hand side. And next we're working with our external rainbow fiber optic system, where we're wanting to use this system to monitor the concentration in real time inside the chamber. So we want to see how much of our API is released out into that chamber. And to do this, we'll use the in situ UV fiber optic probes, which come with the system. And these are slightly smaller in diameter than the standard probes that come with the R6, and these fit inside the SCISSOR platform. And these are fixed path length tip probes with 10mm path lengths. So we can see here, just pulling the SCISSOR fiber optic probes through the back of the system and out into each of the chambers. There's a very small designated port for each of these fiber optic probes in the lid of the chamber. For the rainbow analysis, we actually use the rainbow software called AU Pro, as this allows for a more sophisticated analysis of the offline data, allowing you to look at more than one API and import standards and things like that as well. So we would want to take our 100% T, our blank, and our dark spectrum in order to make sure that the system is working properly before taking our standards and making sure that we build that calibration curve of known concentrations that we can work against in order to quantify concentration with the rainbow system. And so with SCISSOR, we normally work in the second derivative spectrum. This allows us to remove any problems with the baseline, any scattering that we may see during the assay with bubbles and things like that, so that we can work with the data. And then when we want to start our assay, we'll come together and we'll put in our assay details, giving the software information like the volumes that you're working with, the concentrations that you're inputting into the system, and then the path length of the tips that we're using, which is 10mm in this case. And the software will use all of this information later on in order to quantify the drug release. So the beauty of Rainbow is we can take measurements very quickly, in situ as well. So we can take measurements down to every 5 seconds, and we can look at our essentially release of the drug from the cartridge environment to the chamber over time throughout the assay. So the Rainbow R6 actually takes measurements throughout the spectrum from 200 to 700 nanometers. But for SCISSOR applications, we actually recommend that your drug has an absorbance between anywhere above 230 to 240 nanometers, up to the 700 nanometers range. And this is because we have sodium azide in the bicarbonate buffer, which tends to have a UV absorbance, which will absorb at the lower end of the wavelength range. And our SCISSOR software is also highly customizable, so we can change the assays, adapt everything for the user needs. We can make the assays longer, shorter, and we can also change the frequency that you take images with the cameras, the frequency that you take samples, whether that be automatically with our robot or manually yourselves. And we can also customize the assay in general, changing things like the stirring speed, as well as inputting the information that would be relevant for the assay as well. Once we've created our method, we're happy with our time series inside that method, we'd go back to the Chambers tab and we'd start our analysis for each of the chambers in turn. This will open the experiment window where you can name the assay and put in your sample details and start the assay inside the window. So when we're ready, we'd start the analysis for each of our chambers in turn, and you can see all of the lights turning on. You can see the lights, the green light specifically for the transmission, and the backlight behind each of the chambers for the imaging. Once the assay is started, we want to equilibrate the system. So we want to make sure that the temperature has reached 34 degrees centigrade, and we want to make sure that the pH reaches 7.4, that physiological pH. We also want to check our LEDs are making sense and they're collecting data as they should be, and we want to do this all within the first 30 minutes before we inject our sample. Once everything is equilibrated, we would take our time zero sample just before we inject our formulation. And this is where we'd get our injectable ready, and we can inject that via the port at the top of the system. And we can do this manually, and we can also do this with an auto injector as well. We normally slow our injections just due to the size and shape of the system, allowing us to get that nice depot upon delivery. And then we repeat that for our subsequent assays as well. Whether that assay is going to be exactly the same formulation again, and we're wanting to do replicate assays, or whether we're wanting to do a side-by-side of 3 different formulations, we can do that with this system as well, as they're completely separately operated. And over time, we may see migration of that depot, we might see solubilization, we may see precipitation or aggregation. Each formulation will act very differently inside the system and may move differently in the system as well. But this is all data that's captured via the SCISSOR. So we're looking at the imaging data, we're looking at the transmission data, which will give us an idea of the precipitation events, those aggregation events, and we're also looking at the release of the API, how much of our sample is actually getting out of the cartridge or the subcutaneous space and to the place that it needs to go, to those blood and lymphatic vessels. And then we're looking at the data. So with our AU Pro, we're looking at the data over time and seeing the release of our API to that outer chamber. And we can quantify, we can look at that in concentration, and then because of the input parameters of the assay, we can also convert that to percentage as well. And then it allows us to look at that release rate, that release curve. And we can overlay those and look at the 3 different assays and see whether we have a triplicate assay with a similar release rate. We can also look at our software as well to see the reliability of the data that we're seeing, see whether the spectra that we're collecting in the standards during our calibration curve are the same as the spectra that we're collecting inside our assay environment, making sure there's no precipitation event or other occurrence with the data set. And the beauty of the system is we can export the data via the AU Pro software when the assay is complete, and we can actually import it into our SCISSOR assay at the end of the assay as well, and export both data sets together into an Excel file or a Word document or even a PDF document as well, in order to collate all of the data together into one final data set. Post-analysis, we can actually open the assay via the SCISSOR software as well, and we can look at all of the assay once it's complete. So we can see all of the conditions, the temperature, the pH, the transmission values, and we can also look at when we did our sampling time points, whether we left any comments, and also our images as well, so we can look through those and see what the assay actually looked like over time. Once we've imported our fibre optic data into the SCISSOR data, we can export them both together via Excel, CSV file, PDF, Microsoft Word, and we can also export the images as well. When we open the Excel file, there will be a raw data tab with all of the raw data taken from the assays. There'll be a results output tab with a neatened version of the datasets with pre-plotted graphs. And there'll also be a stability tab with all of the data during the equilibration phase. And lastly, the fibre optic tab will then be populated with all of the data taken via the fibre optics with the Rainbow R6 system. And this would allow us to take that data and to compare our formulations, to rank order them, and decide which formulations are better than others. Users of the SCISSOR and R6 will then take this data in order to get a better understanding of the formulations and the characteristics of those formulations, to see whether they had any precipitation events or degradation events occurring over time, whether there was any correlation between the release data and the precipitation data seen, and to rank order their formulations or to excipient screen between those formulations as well. And this will help them narrow down their formulations, deciding which formulations to take forward to that next stage of development. Thank you for your attention, and we'll now move forward to the Q&A section of this webinar.